Good morning. Today, we are going to look at gypsum products in dentistry. We are going to be looking at the different types of gypsum products, how they are manufactured, the setting reaction, different types of setting expansion, the strength, properties, manipulation, and applications of gypsum products. Gypsum products refers to the various forms of calcium sulfate, hydrous and anhydrous, that are manufactured by calcination of calcium sulfate dihydrate, which occurs as a mineral gypsum. The ADA specification number of gypsum products is 25. Gypsum products can be classified as type 1 impression plaster, type 2 dental plaster, type 3 dental stone, type 4 die stone high strength low expansion, type 5 die stone high strength high expansion. The first one, type 1, is impression plaster, which is basically used for making preliminary impressions while constructing complete dentures. Type 2 is dental or model plaster, which is beta calcium sulfate dihydrate. The powder particles are large, porous, and irregular. It is relatively weak and has a compressive strength of 9 MPa and a tensile strength of just 0.6 megapascals. They are used in fabrication of study models, in flasking of dentures, mounting of casts in an articulator, etc. Type 3 dental stone is alpha calcium sulfate hemihydrate. The powder particles of this are relatively more regular in shape. They are non-porous and require relatively smaller amount of water for mixing. They are used for making models and casts in dentistry. Type 4 dental stone is also called die stone, high strength and low expansion die stone. And the principal requisites are sufficient strength, hardness, abrasion resistance, and a minimal setting expansion. They are used as a die stone material, and they're used for inlays, crown and bridge wax patterns for preparing dies for these procedures. Type 5 die stone has a high strength and also exhibits high expansion. The improved strength is obtained by lowering the water powder ratio. The setting expansion has been increased to 30%, and this expansion is required for the die to compensate for the shrinking of the alloy. For making dies, when there is inadequate expansion, then the fabrication of cast crowns also becomes defective. Let us take a look at the manufacturing of gypsum products. Plaster and stone products are produced by a process called calcination, the calcining calcium sulfate hemihydrate. The gypsum product is ground and is subjected to temperatures of 110 degrees to 120 degrees to drive off part of the water of crystallization. And as the temperature is further raised, the remaining water of crystallization is removed. So let us take a look at the reaction that happens during the process of calcination. On heating gypsum products, the following changes take place at different temperatures. At a temperature between 110 to 130 degrees centigrade, the calcium sulfate dihydrate gets converted into calcium sulfate hemihydrate. On further heating up to temperature of 200 degrees centigrade, it changes into calcium sulfate hexagonal anhydride. And on further heating up to a temperature of even 1000 degrees, it becomes orthorhombic anhydride. So the basic crystal structure changes. Calcination is of two types. It can be dry calcination or wet calcination. When the gypsum ore is purified by washing, drying, and powdering. Then in an open pan or kettle, which is open to the atmosphere, it is heated to a temperature of 110 to 130 degrees centigrade. Then most of the gypsum gets converted into the hemihydrate form. When it is heated like this in an open kettle, which is open to the atmosphere, the crystal type produced is beta calcium sulfate hemihydrate, which has a monoclinic lattice, and the crystals are spongy, irregular, and large. This is the method that is used to manufacture type 1 and type 2 gypsum products. That is, dry calcination is the method used to produce impression plaster and dental plaster. The other type of calcination is called wet calcination, when this purified gypsum is heated under steam pressure to about 110 to 130 degrees centigrade in a closed kettle or a rotary kiln or an autoclave. The calcium sulfate hemihydrate, which is formed, has a prismatic monoclinic small crystals. This is called dental stone, hydrocal, or autoclaved calcium sulfate hemihydrate. So this is the method that is used to produce alpha calcium sulfate hemihydrate or dental stone. Alpha hemihydrate, alpha modified hemihydrate, and beta hemihydrate. Now, these are the three types of the gypsum products that we get after the different forms of calcination. Alpha hemihydrate is called artificial stone, dye stone, or improved stone, which consists of smaller, regularly shaped crystalline particles in the form of rods or prisms. Alpha modified hemihydrate is made by boiling gypsum in a 30% aqueous solution of calcium chloride and magnesium chloride. This process yields the smoothest, most dense powder particles of the three types, and this is the one that is primarily used for dyes. Beta hemihydrate, which is dental plaster, consists of large, irregularly shaped orthorhombic crystal particles with capillary pores. Taking a look at the setting reaction of gypsum, when calcium sulfate hemihydrate is dissolved in water, a saturated solution of calcium sulfate is formed, and subsequent aggregation of the less soluble calcium sulfate dihydrate, and then there is precipitation of the dihydrate crystals. Okay, so that is when calcium sulfate hemihydrate combines with water, it forms calcium sulfate dihydrate with the release of heat. The reaction is exothermic. Then the set gypsum consists of dense, interlocking, needle-like crystals, which are called spherulites. How does the setting reaction happen? There are different theories regarding this. The first theory is the colloidal theory, the next, the hydration theory, and the most accepted theory is the dissolution precipitation theory. The colloidal theory states that when mixed with water, the gypsum enters into the colloidal state through a sol-gel mechanism. In the stall state, the hemihydrate particles are hydrated to form dihydrate, and they enter an active state. As the measured amount of water which is available is consumed during the setting process, the entire mass converts into a solid gel. The hydration theory occurs that the plaster particles join with each other through hydrogen bonding to the sulfate groups, and they form the set materials. Both these theories are not widely accepted and have been rejected. The theory that has been accepted is the dissolution precipitation theory. In this, when calcium sulfate hemihydrate is added to water, it dissolves and forms a solution whose solubility is 1/4. Okay, then calcium sulfate dihydrate is formed. The solution becomes supersaturated with the dihydrate. Then the dihydrate precipitates and on the already present calcium sulfate dihydrate, and nuclei begin to crystallize. Continuous precipitation causes crystal growth like star-like spherulite structures, which begin to intermesh, increasing the viscosity of the mix. The thick mix is in the moldable state. After some time, it becomes friable, soft, solid. And then the excess water is suddenly drawn inside by capillary action with loss of gloss, and gradually it becomes hard. Strength increases with respect to time. When the powder is mixed with water, the time that elapses from the beginning of the mixing till the material hardens is called setting time. The setting time can be divided into initial setting time and final setting time. The initial setting time is the interval between the time the water and the powder are mixed with each other up to the time that the mix can no longer be poured into a mold or an impression. Clinically, this initial setting time can be observed when the freshly mixed material loses its gloss. Chemically, the loss of gloss occurs because the chemical reaction of hemihydrate uses up all the water, and the surface water is drawn into the bulk of material by capillary action. Gypsum should not be manipulated after the initial setting time because it is still weak and it can often fracture. The initial setting time is usually within 8 to 16 minutes. The final setting time is the time at which the material can be separated from the impression or the mold without any distortion or fracture. How do we measure this setting time? Different methods of measuring the setting time are the loss of gloss method, the exothermic reaction, and by penetration tests using penetrometers like the Vicat needle and the Gilmore needles. Like I said before, as the setting reaction proceeds, the gloss disappears from the surface of the mixed gypsum product because all the water gets drawn in through capillary action. This shows the initial setting of the material. As the material sets, the reaction is exothermic with the production of heat. So we can feel the warmth from the set material. The initial Gilmore test is for the initial setting time of gypsum products. There are two Gilmore needles. The smaller Gilmore needle is also called the initial Gilmore needle. Now, the mixture of mixed gypsum is spread out and the needle is lowered onto the surface. The time at which the small Gilmore does not leave an impression is called the initial set. It's also called the initial Gilmore. The smaller Gilmore has a weight of 1/4 pounds and a tip diameter of 1/12 inch. The Gilmore test for final setting time. In the next stage, the setting process is measured by the use of the heavier Gilmore needle. The elapsed time at which this needle leaves a barely perceptible mark on the surface is called the final setting time. The bigger Gilmore needle has a weight of 1 pound and a tip diameter of 1/24 inches. The next penetrometer test for setting of gypsum product is called the Vicat needle test. The needle with a weighted plunger rod is supported and held just in contact with the mix soon after the gloss is lost. The plunger is then released. The time elapsed until the needle no longer penetrates to the bottom of the mix is called the setting time. A Vicat needle has a weight of 300 grams and a tip diameter of 1 millimeter. What are the factors which affect the setting time of these gypsum products? Some of the factors are the water powder ratio, the temperature, accelerators and retarders, impurity, and the fineness of the material itself. Water powder ratio is an important factor in determining the physical and chemical properties of the final gypsum product. If the water powder ratio increases, the setting time increases, but the strength of the gypsum product decreases, the setting expansion also decreases. More the water used for mixing, the fewer nuclei there are per unit volume. So the setting time gets prolonged. But increasing the water powder ratio is never a good idea for increasing the working time or the setting time of gypsum, because the strength of the material will be sufficiently lower. The effect of temperature on the setting time is likely to be erratic and can vary from one gypsum material to the other. Okay, little change occurs between 0 degrees centigrade up to 50 degrees centigrade. If the temperature of the plaster water mix exceeds this 50 degrees centigrade, a gradual retardation in the setting occurs. And as the temperature approaches 100 degrees centigrade, no reaction takes place. Higher the temperature, the smaller is the ratio of solubility of the dihydrate and hemihydrate, resulting in a slower and longer setting time. Higher temperature causes greater degree of mobility of the ions participating in the reaction, which results in faster reaction and shorter setting time. Let us take a look at the common materials which are used as accelerator and retarder. When a chemical which is added decreases the setting time, that material is called the accelerator. And if it increases the setting time, it is called the retarder. The setting time can be accelerated by adding some more gypsum or potassium sulfate or sodium chloride. And the setting time can be retarded by adding organic materials like glue, gelatin, and gum, or by adding borax, potassium citrate, or 2% sodium chloride. So these are the accelerators and retarders of gypsum products. Like I said again, gypsum, potassium sulfate, or sodium chloride are the accelerators, whereas glue, gelatin, gums, borax, potassium citrate, and sodium chloride are retarders. Impurities act as accelerators of the setting time. If the calcination is not complete and the gypsum particles remain, or if the manufacturer adds more gypsum, then the setting time is shortened because of the increase in potential nuclei of crystallization. The finer the particle size of the hemihydrate, the faster the mixture hardens. The next topic that we are going to look at is the setting expansion of the gypsum products. Gypsum products exhibit two types of setting expansion. The first is the normal setting expansion, and the second is called the hygroscopic setting expansion. Let us take a look at what is this normal setting expansion. The crystallization process is pictured as an outgrowth of crystals from the nuclei of crystallization. Now, because of the entanglement of the dihydrate crystals, the crystals growing from the nuclei, they intermesh with each other and they obstruct the growth of adjacent crystals. So, as the gypsum sets, a little bit of expansion does take place, but this expansion is measured and it is limited. So, because there is impingement and movement in the movement of the micropores. The setting expansion can be controlled by increasing the spatulation, which increases the setting expansion, Increase in water powder ratio, however, reduces the setting expansion. Modifiers generally reduce the setting expansion. Potassium sulfate 4% reduces the setting expansion from 0.5% to 0.06%. Sodium chloride and ground gypsum, however, increase the setting expansion. The other type of setting expansion is called hygroscopic setting expansion. That is, the setting expansion can be increased by immersing this material in water when it is setting. Now, and like I told you before, when it is in air, the surface tension of the water, it draws the crystals together and inhibits an outward expansion of the crystals, resulting in a limited setting expansion. However, when the material is immersed in water, the crystals can grow more freely, and the water of crystallization is being continuously replenished. This results in a greater degree of expansion, and this process is called hygroscopic setting expansion. So you see the basic differences between normal and hygroscopic setting expansion. In the initial mix, in normal setting expansion, where the hemihydrate gets surrounded by water molecules, then water around the particles gets absorbed into the gypsum product and the water gets reduced, the particles are drawn closer. Finally, when the water around the particles get exhausted due to the hydration of the gypsum, the crystals will shrink, which is opposed by an outward thrust of crystal growth. The crystal then become more entangled and intermeshed with each other, and this inhibits the expansion to a large extent. The crystals in the terminal stage undergo further entangling with each other. So in the normal setting of gypsum, the different stages of setting are the initial mix, the initial crystal growth, the solid phase contact, the expansion, and the termination. In normal setting expansion, the expansion is limited because of the limited availability of water of crystallization and the surface tension, which tends to pull the crystals towards each other. This surface tension is opposed by the outward growth of the crystals, but there is only limited setting expansion. Whereas in hygroscopic setting expansion, the hemihydrate is surrounded by excessive water molecules. Since the water of hydration is continuously replaced by other water molecules, the particles remain at the same place. In the solid phase contact stage, the lost water molecules are again replaced by new water molecules. So the outward growth of the crystals is not opposed by the shrinkage, and the particles separate as the crystal continues to grow. This intermeshing of crystals take a long time, and hence expansion goes on undisturbed. Even during the termination stage, the crystal expansion can continue without any disturbances. That is why hygroscopic setting expansion is definitely much larger than the normal setting expansion. The strength of gypsum product increases rapidly as the material hardens. There are two types of strength which we measure, which is called the dry strength and the wet strength or green strength. When the excess water in the specimen has been driven off by complete drying of the material, the strength that we obtain is called the dry strength. Excess water from the cast may be removed by low temperature drying or open air drying. The wet strength is the strength obtained with the water in excess of that required for hydration of the hemihydrate is left in the specimen. The wet strength of dental plaster is 9 megapascals, and for improved dental stones is 35 megapascals. Let us take a look at the manipulation of these gypsum products. The mixing time is defined as the time from the addition of the powder to the water until the mixing is completed. Mechanical mixing is completed in around 20 to 30 seconds. The working time is the time available to use a workable mix, one that maintains a uniform consistency. It is measured from the start of the mixing point to the point where the consistency is no longer acceptable for the products to be poured into a mold or an impression. The strength of the stone is inversely proportional to the water powder ratio. The water and powder should be measured by using an accurate graduated cylinder for the water volume and a weighing balance for the powder. This is a chart which shows the recommended water powder ratio for the different gypsum products. For impression plaster, it is between 0.50 to 0.75. For dental plaster, 0.45 to 0.50. For type 3 dental stone, it is 0.28 to 0.30. For improved stone, it is 0.22 to 0.24. For type 5 die stone, it is 0.18 to 0.22. How do we manipulate these gypsum products? We take a measured amount of water in the bowl and then we sift the weighed powder into the water and initial hand mixing is begun. The mix is then vigorously stirred, periodically wiping the inside of the bowl with a spatula to ensure the wetting of all the powder particles and the breaking up of any agglomerates or lumps. Mixing is continued till a smooth mix is obtained, usually within 1 minute. A longer spatulation time will drastically reduce the working time available. Once the cast is obtained from the impression, we always check that the cast is an accurate reproduction of the oral tissues. And any departure from the expected accuracy will result in a poorly fitting prosthesis. When a dry cast is immersed in water, negligible expansions occur if the water is saturated with calcium sulfate. If it is not saturated with calcium sulfate, the gypsum can be dissolved into the water. If the stone cast is immersed in running water, its linear dimension may decrease approximately 0.1% for every 20 minutes of immersion. The safest method of soaking a cast is to place it in a water bath in which plaster debris is allowed to remain consistently at the bottom of the container to provide a saturated solution of calcium sulfate. Storage of either set plaster or stone at room temperature produces no significant dimensional stage. If the storage temperature is raised between 90 degrees centigrade to 110 degrees centigrade, shrinkage occurs as the water of crystallization is removed and the dihydrate reverts back to the hemihydrate stage. For mixing of gypsum and plaster, the latest method is the vacuum mixing, mechanical mixing under vacuum, which removes all the air bubbles created during mixing and evacuates any potentially harmful gases. Air bubbles that remain in the mix can be entrapped on flat and concave surfaces that are not oriented for air evacuation. Tilting results in releasing the air bubbles to the surface. Excessive vibration, however, should be avoided because it causes the solids in the powder to settle and may lead to free water accumulation, resulting in surface roughness. Models, casts, and dies can be disinfected with a spray of iodophore used according to the manufacturer's instruction, or they can also be disinfected by immersing them in a 1:10 dilution of 5% sodium of hypochlorite solution for 30 minutes. Gypsum products are used in dentistry for the preparation of study models, for oral and maxillofacial prosthesis and as important auxiliary materials for dental laboratory operations, which are involved in the production of dental prosthesis. The different types of dental plaster can be used to form molds and casts on which the prosthesis and restorations are constructed. Dental stone is mixed with water, poured into impression, allowed to set, and this hardened impression material serves as a mold to form a positive model master cast or die. Let us take a look at the different potential questions that can pop up from this chapter for your examinations. You can be asked about the different types of gypsum products used in dentistry, the uses of each type, the manufacturing process of gypsum, the manipulation technique of gypsum. Okay, these are some of the questions that have been found in the university exam papers. So with this, we come to an end of our lecture. I hope you have got a clarity about the subject, the different types of gypsum products, the strength, the properties, the manipulation, and the application of gypsum products. Thank you.